So, short video lesson on relationships and graphs in general, including real-life graphs. So in algebra if we could divide everything we have to learn in algebra under three headings. One is about handling expressions, Secondly, about relationships, which we could also refer to sometimes as either rules or functions or formulas, showing how different things are related to each other. And finally, the other main heading in algebra is equations and equation solving. So here we're looking at relationships and graphs in general, including real-life graphs. We have a girl here, and what has happened, on each of her birthdays, her father has recorded her height on the door frame. So there's a mark on the door frame recorded on each of her birthdays. So what's then happened is that these heights have been recorded on a graph. So for example, on her first birthday, she was 70-something centimeters tall. On her second birthday, she was 83, whatever it is, centimeters tall. On her third birthday, 90 or 91 centimeters tall. So these heights have been plotted as points, and then they've been joined together by small straight lines to create this sort of curve effect. There is a relationship between the girl's age and her height, but the relationship may be difficult to describe using GCSE math. So we have different mathematical expressions, and if we try to find one that will describe that curve, it may be tricky. Let me show you what I mean by that. Here's an expression, a linear expression. A linear expression will give rise to a straight line linear graph like this. So that wouldn't be any use for describing the change in the girl's height, because it's clearly, the graph we were looking at a moment ago clearly isn't a straight line. A square expression, like x squared plus 8x plus 15, that changes in value like that, and that creates a valley-shaped graph, and that wouldn't be appropriate for describing this relationship. A cubic expression like x cubed changes in value, something like that. Apologies for the curve not being perfectly drawn, but that's the best I could do. So a cubic expression gives rise to a curve like that, and so none of those three expressions can be used to describe the way the girl's height changes. It's quite a particular curve there. So what we can do though is we do have the graph that describes it, and we can still use the graph, but we just have to acknowledge that we can't find a mathematical way of describing that relationship. There are other graphs where we can still use the graph, but we can't find a mathematical expression to describe it. So here, for example, is a race being run between Nina and Polly. This line shows Nina's progress in the race, and the dotted line shows Polly's progress. So what it means is at the beginning of the race here, it was Nina who made the fastest start in the race. So after 10 seconds, she'd gone further down the course than Polly had. What happened at the 22nd point, the two runners would have been neck and neck, and that's where Polly would have overtaken, and then through this point here, Polly is in the lead. And then what happened right very near the end of the race is that again, just there, they are neck and neck, and Nina is in the lead after this point. So you need to get used to reading graphs. Even though we can't describe them mathematically, we need to be able to interpret them and understand what they're telling us. Another graph, this is a distance time graph showing somebody cycling, and it shows the distance from Newcastle. Here the person is cycling away from Newcastle, cycling 16 miles. This part of the graph here, the person isn't moving, and then the person resumes their cycling, and here they are 20 miles from Newcastle. They must be at Ashington there, and that's going to be about 1:30. And this is some graphs potentially to do with the filling of a bottle. So there's the shape of the bottle, and we have to identify which graph describes the change in height as water is poured steadily into the bottle. So when the bottle is initially filling it up, water is initially filling up the bottle, the water level will rise steadily, and that probably means that the kind of graph it could be that graph there, that one. When at time zero, I believe the bottle would be empty. So I don't think we can be looking at that one. So it could be this. There's going to be part of the time in this middle part where the water is filling up here, where the graph may curve slightly. In the last part of the filling process, the water level will rise quite quickly because the container is narrower. The water level will rise more quickly than it did down here. So we want a graph where the water level initially rises slowly, but then in the last part it rises comparatively quickly. So it may well be that this one is the right graph to describe it. So here we have a water level rising slowly, and then in the last part the water level needs to rise more quickly because the diameter of the container is less. So this is either this one, or could it be this one? No, it can't. We need the water level to rise slowly initially and then more rapidly. Another distance time graph. So we have this is a journey of a train between two stations. The stations are 6 kilometers apart, so it looks like the train was traveling at a steady speed, then it was stopped maybe at a station, and then it resumes its journey and it arrives at the other station 6 kilometers apart. The two parts of the journey, in which one is the train moving faster? This line here is steeper than this one. In this part of the journey, in 4 minutes it covered 4 kilometers, but here in 4 minutes it only covered 2 kilometers. So here, in this part, the first part of the journey is faster than the third part of the journey. This part up here. So you can use the gradient or the steepness of the graph of the line to tell you about how quickly something is happening, the rate of travel or the rate of filling up the container. Another progress on a sponsored walk. Walking, stopped, walking, stopped, walking. The steepest part of the graph, I think, is this one here. That's the flattest or shallowest part of the graph. That will be when she's walking the slowest on the last leg of the journey. So starting off at a moderate speed, then getting a little bit faster there. That line segment is steeper than that, and the last part is the flattest. So she's obviously running out of energy. Maybe, I don't know. Train journey. The train journey. This one here, the line returns back. It kind of goes. We have the initial journey, then the train is stopped, then the journey continues, and then stopped, and then the line comes back. So what must be happening here is the train is travelling 100 kilometres from its start. Starting point, it will travel 50 kilometres, stops, continues until it's 100 kilometres from its start. But then this line here is showing that the train is returning to where it started from. Which part of the journey is faster, from A to B or from C to D? From A to B or from C to D? The steepest part of the graph is this one. The fastest part of which part of the journey is faster? This part of the journey is faster than this part. How far did the train travel altogether? Well, it travelled 100 kilometres away from its start, and then it returned back along. This is it returning to where it came from. So it must have travelled 200 kilometres in total. And the speed, the average speed of the train for the whole journey, it covered 200 kilometres, and it did that in 5 hours. So if you 5 hours for the whole journey, the average speed for the whole journey. So covering 200 kilometres in 5 hours, that would be the same as if it covered 40 kilometres in 1 hour. So the average speed is 40 kilometres per hour. I think that will do. Thank you.